Everyone, I hope you are doing well. My paper topic is application of neural network in design of model reference control, iterative learning control. The content of this presentation is problem definition, motivation and objective, literature review, novelty and contribution, methodology, results and discussion, and finally conclusion and references. Problem definition. There are three stages involved when using artificial neural network-based iterative learning control framework. The first one is system identification. System identification includes designing a neural network model of the plan. The next one is control strategy. A neural network controller is designed which can be improved using backpropagation technique. In this study, to do system identification and controller design, the model reference controller method is used. So as the name suggests, in this case, we will have our reference model, and then we will design controller that will control our plan to follow that reference model. A tuning section at the final stage can be update neural network parameter after each trial. Motivation of doing this work is first, nowadays system designers are highly interested in intelligent control techniques because of complexity of dynamical system has have increased. In addition to this, the great majority of existing iterative learning control schemes still require a mathematical model of the plan to properly design the control signal. Also, engineering research focuses on developing more accurate control techniques which can adapt to changing environments and uncertainties. This method is an effective control strategy to solve tracking control problem. Also, the strategy improves the control performance during each trial. The literature review. Effective learning control is an effective data-driven method for improving the control signal, initially proposed in 70s and has usage in different areas. Nowadays, it has established as a separate field of control theory, and these machine learning techniques prove its usefulness in many real-world engineering applications, such as mentioned studies. Artificial neural network based iterative learning control have been intensively studied during the last 3 decades and proved their usefulness in a control theory. In terms of novelty, the first is merging model reference control with iterative learning control. The purpose method was tested and offered excellent performance for three dynamic system with high level of nonlinearity. The next one is alleviating the computation cost, and finally, it is a great method for applying to repetitive tasks. A methodology of this work, iterative learning control become an attractive method to improve the system performance in the context of repetitive process which can be found frequently in an industrial process. Generally, iterative learning control enhance the quality of control strategy using a self-tuning process during the learning and can be applied to many industrial applications. The strength of iterative learning control is to utilize the process information and comprising on a historical data and to improve the tracking performance on every trial, as you can see in a figure number 1. Mm, Multi-layer neural network have been applied successfully in identification and control of dynamic system. There are three common neural network controller: model predictive control, NARMA L2 control, and model reference control. These controllers are representative of the variety of common way in which multi-layer neural networks are used in a control system. I selected model reference control model because of its lower computation load. As I said in the problem definition, there are typically two steps involved when using neural network for control: system identification and control design. We want to develop a neural network model of the plant we want to control, and then we use the neural network plant model to design or train the controller in a control design stage. So the first stage of the model reference control is to train a neural network to represent the forward dynamic of the plan. The prediction error between the plan and neural network output is used as a neural network training signal. The process is represented in figure number 2. And figure number 3 is the structure of neural network plan model, and where the block labeled TDL are tapped a delay line that store previous value of the input signal. The plan model is identified first, and then the controller is trained so that the plan output follows the reference model output. The idea is to update neural network controller parameters after each trial according to update rule. As it is shown in figure number 5, first we have a plan for which we will create a neural network plan model. Then we have a neural network controller block, and it has 3 input: delayed reference input, delayed controller output, and delayed planned output. While there are two set of inputs to the neural network plan model: delayed controller output and delayed plan output. And the practical implementation of the framework is demonstrated on 3 nonlinear system application: a magnetic levitation system, a robot arm, and a continuous stirred tank reactor. Uh, The objective of the first application is to control the movement of a single link robot arm, which is depicted in figure number 6. The robot used in this present research is a single link arm with 1 rotational degree of freedom. The dynamic of this robot arm is given, and which is a reference model that we like our robot follow. As you can see, the dynamic use the torque which is supplied by the motor. So in this case, we will have 2 neural network. First will be for plan, and the second for controller. The figure number 7 on the screen shows how controller will look like when built on Simulink. By opening the plant on Simulink, we can see these are the same equation governing by the motion of the robot arm. By right click and opening the controller, we can see neural network model and neural network controller. The neural network plan consists of basic time series model of our plan, and neural network controller comprised, as already said, we have 3 input. By doubling click on the controller, we can see below window as the model reference control model method is used here in figure number 8. So as the first step here, we can click and identify the plan. After that, by clicking on generating training data, the data will be generated, is input, and target for creating a neural network plan model, as you can see in figure number 9. After model identification, we come back to the window of model reference control to terrain controller. After completing all and running the Simulink model, we can see 2 signal, the red in figure number 10, and the red is a reference signal, and the blue signal is the output of our plan. As we can see, the blue line is trying to follow the red line. The error autocorrelation function is used to validate the network performance. It describes how the prediction error is related in time. Better to have a non-zero value of autocorrelation function, and it should be occur at 0 lag. Also, the input error cross correlation function is used for more verification of our model performance. In this input, the correlation error is acceptable, and also it should be possible to improve that, perhaps by increasing the number of delay in the taps line delay line. As I said, in this case, all of the correlation fall within the confidence bound around the 0. I applied the result to other case study with high level of nonlinearity, as I explained for the robot, and I produce acceptable result and complete result for all three models will be presented in a paper. And the next model is the case studies continuous started tank reactor. And in terms of conclusion, the presented results show the neural network modeling can be successfully applied to the setting of iterative learning control, leading to significant improvement of control system performance. Clearly, the decided advantage of the proposed approach are a great flexibility of neural controller in adaptation to plan nonlinearity and simplicity of the ultimate training algorithm. Also, this method provides designer with the opportunity to improve the system modeling. Thank you so much for your attention.